You know, some of the biggest facts we learn about data structures and algorithms, well, they're not exactly true. At least, not the whole truth. Today, we're going to bust the myths that can silently break your code and maybe even tank your technical interviews. All right, let's get into it. So let me kick things off with a question for you. Is an n-squared algorithm always slower than an n log n1? Now, if your gut reaction was, yeah, of course it is, then you are definitely going to want to stick around for this. The real answer, as we're about to see, is a whole lot more interesting. We're going to be debunking some of the most common myths in the world of data structures and algorithms. We're going to focus on 3 huge ones today, and you'll see pretty quickly that these aren't just for academic debates. They have major real-world consequences. We're going to tackle these so-called guaranteed O1 speed of hash tables. We'll get into what big O really means for performance, and we'll unravel the deceptive simplicity of binary search. I promise, by the end of this, you'll have a much smarter, more practical way of thinking about these fundamental tools. Okay, first up, let's talk about an absolute classic, a developer favorite, the hash table. And the myth around it is all about that legendary speed. You've heard it a million times, right? Lookups, inserts, deletes in a hash table are constant time, O of 1. And yeah, that's the dream, that's the goal, but it is absolutely not a guarantee. And the reason why it's not guaranteed, it all comes down to one single crucial idea. And that idea is the hash collision. This is what happens when your hashing function takes 2 totally different keys and, oops, maps them to the exact same spot in memory. When that happens, you can't just overwrite the data. You have to handle it, usually by starting a little list or a chain right there in that one bucket. And this is where things get really dramatic. Look at the difference here. In the best, most common case, your keys are spread out nicely, and lookups feel instantaneous. It's beautiful. But in the absolute worst case, say someone intentionally feeds you keys that all collide, your beautiful hash table just degenerates into a slow, clunky linked list. And your lookup time? It skyrockets from O1 all the way to O of n. So the real key is this little symbol here, alpha, the load factor. It's just the ratio of items you've stored to the number of available buckets. The actual, more accurate time complexity is O of 1 plus alpha. As long as you keep that load factor low, you stay super close to O of 1, but it's never ever a blind guarantee. You know, this whole idea of it depends is the perfect segue into our next big myth. This one's about the very meaning of big O notation and how we often misapply it in the real world. And here it is, the one we started with. The idea that an algorithm with a better big O, like O(n) log n, is just plain faster than one with a worse big O, like O(n) squared. This is one of the most dangerous oversimplifications in all of programming. And this chart just shows it perfectly. Look at this. For really small arrays, the theoretically slower insertion sort is actually faster than merge sort. How is that possible? Well, it's because big O is all about long-term trends. It completely ignores the constant factors, the setup costs, if you will. And those costs can easily dominate when your input size, n, is tiny. But of course, as n gets bigger, the story totally flips. That n-squared term in insertion sort just explodes, and merge sort's superior scaling takes over and leaves it in the dust. This is exactly why a lot of the best sorting libraries out there, like Python's timsort, are actually hybrids. They use a simple sort, like insertion sort, for all the tiny subproblems. This really is the bottom line. Big O tells you how an algorithm behaves as n approaches infinity. It does not tell you which one is faster for the specific data you have right now. Context and constants are king. Okay, for our last myth, let's switch gears a little bit, from raw performance to correctness. This one is about an algorithm that looks so simple on the surface, but has famously tripped up even some of the best programmers in the world. Binary search. It's one of the first really clever algorithms we learn, right? The whole divide and conquer thing is so elegant. But that simplicity is a trap. Tiny, almost invisible bugs in a binary search implementation can lead to massive, hard-to-find problems. And hey, don't just take my word for it. This is a famous quote from Joshua Block, a legendary engineer from Google and Sun. Back in 2006, he wrote this amazing blog post about a subtle bug that had been hiding in plain sight for years in countless standard libraries, including Java's. And the culprit? A simple integer overflow. The whole problem is right here, this line of code. Mid equals low plus high divided by 2. It looks totally harmless, but if low and high are really big numbers, like, say, indices in a massive array, their sum can actually exceed the maximum value for an integer and wrap around to a negative number. The fix is so simple but so clever. Calculate the range first, high minus low, and then add it to the base. You get the same result, but you completely avoid that overflow risk. It's a tiny change that makes all the difference. So, we've busted a few myths. What should we use instead? Let's pull all these lessons together into a new, smarter set of principles for how we should really think about algorithms. Here's your new toolkit. First, always state your assumptions. Are we assuming a good hash function? Second, remember that constants and cutover points matter. Big O is not the whole story. Third, don't just talk about the average case. Always think about the best and, more importantly, the worst case scenarios. For tricky stuff like binary search, think about the core truths, the invariants that have to hold. And finally, remember the golden rule. The best algorithm always depends on the shape and size of your actual data. And that really brings us to the end. I want to leave you with one final thought. It's really easy to just lean on these simple rules of thumb we all learn, but true expertise, true mastery, comes from knowing when and why to question them. So, my challenge to you is this. Take a look at your own code. Which so-called fact that you've always taken for granted might just be a myth waiting to be busted?